Hi there! Welcome to a new physics lesson filled with adventure and discovery. Today, I'm going to go over a couple of the projectile motion practice problems on your worksheet because I realize that they are pretty difficult, and so I want to give you an example of each of the main different types of problems you'll face when in this chapter for projectile motion. So on your worksheet, we'll be doing numbers 1 and number 1 and 4 for your practice worksheet, just to get you started. Like I said, there's two main projectile motion problems. There's one in which a projectile is launched horizontally, like straight off the cliff or straight off the table. There's no y component at all. There's only initial x component. There's no initial y component. So I'm going to do one of those problems. That's the example 1 on your worksheet. And then second of all, I'm going to do a problem where there is a y component, where something is like launched from ground level, like that in my point, like my red pointer. Or in this case, number 4, in which a football player, a punter for a football team, punts a ball a certain distance. And so let's get into it. So here's our first problem. We have a stone thrown horizontally off the cliff 15 meters per second, and it goes 44 meters high. It travels negative 44 meters. And we want to find the distance or the range that rock traveled. And so if you look on your equation sheet under projectile motion, which is the second column, you'll notice that about halfway down we have the vector component equations up above, but halfway down we have x and y. And if you notice, we're always, whenever we have a projectile motion problem, we have to split it up into x and y components to make it easier for us to solve the problem. So notice for our x component, we have one main equation we're going to be using. Since there's no x acceleration whenever we have projectile motion, and so because of that, we can use that equation delta x equals vixt. For the y component, however, there's 3 different free fall equations we could possibly use. But for this case, since we're looking at how far from the base, that is going to be in the x dimension. We're going to call it the x dimension. Some givens that we can take from the problem. First of all, is that our initial velocity in the x direction is 15 meters per second. It's all in the x direction. We don't have it shooting downwards at all. It's all in the x direction. Our acceleration in the x direction is 0 meters per second. How about in the y? In the y, our initial velocity is going to be 0 meters per second, and then our acceleration is going to be a constant negative 9.81 meters per second squared, our gravitational acceleration constant. However, we just want to find this, and so we're going to be working in the x-axis, and we have that one equation, delta x equals vit. However, if you notice, we want to find delta x. We have the initial velocity in the x direction, vix. However, we don't have time. So we're missing 2 variables. We cannot solve this right away. We have to solve for time first. And so in order to solve for time, we're going to have to use a y component or y dimension to solve for time. And so if you look at your 3 equations for the y dimension, we have 2 equations that we could solve for time in. We don't have the final velocity at this point. We can't assume that it's 0 because we're going to calculate for it right before it hits the ground. And so we're going to have to actually use the second equation, which is delta y equals viyt plus half at squared. In this case, a is gravity. And again, we can use that second equation because we do not have the final velocity in the y direction. And so if we calculate for this, plug in our numbers, we know that delta y is negative 44. We know that our acceleration due to gravity is negative 9.81. And here's another kind of pointer. We also cannot use that first y equation because we're given the delta y. And as I mentioned in the last chapter, if we're given a certain value, we're going to have to end up using it in our equation. And so we have negative 44 is equal to, and notice my initial velocity in the y is 0 because it's just shooting straight off. It's not shooting downwards at all. So we're going to solve for this. Simplify our equation. Okay, multiply both sides by 2 to get rid of that half, and then divide by negative 9.81 to get 8.97 meters equals, okay, actually it's not going to be meters, but we're going to take the square root to get our time. Our time is going to be 2.99 seconds to fall all the way down here. Okay, and so now we can plug that number into our equation here, and so we have that, and so we plug that in for our time, we calculate for that, delta x is going to be equal to 44.85 meters. And just thinking about it, if we, let's say you did use that first equation on accident, if you assume that initial velocity is 0, and you also assume that final velocity in the y dimension is 0 because it hits the floor, then all you're left with is gravity and time, which you cannot solve for either one of them. So that first equation just falls apart. We're forced to use that second equation. Okay, so that's how to do this first example problem. Half of the problems in projectile motion are going to look like this, where it just shoots straight off, and you have to use mainly this equation. You're going to use a y equation to supplement or solve for time, or to solve for mostly the time. Okay. Second example problem is, well, what if you have a projectile that's launched from ground level and it has x and y component like this one? So number 4, look at number 4. Scoot to number 4 on your worksheet. Second type of projectile motion problem. We have a football player and he kicks a football from the ground level with an initial velocity of 27 meters per second. Okay, so that's a diagonal velocity. And that velocity is 30 degrees above the horizontal. We want to find the maximum height of that kick. We want to find how long it takes the ball to return to launching height, so basically the ground, or the same level he kicked it at, and then how far away did it land, the range. So before you do anything, because we have a diagonal like this, we have to split it up into x and y components. So to do that, we use our geometry. To find this y component, we take our diagonal times sine of the angle. To find the x component, we take the diagonal times cosine of the angle. And so we get those two numbers. Our initial velocity in the y direction is going to be positive 13.5 meters per second. Our x velocity is going to be 23.4 meters per second. Our acceleration in the y-axis is always negative 9.81 meters per second squared. And then our our acceleration in the x direction is going to be 0. Our velocity is going to be constantly that number. And so we're going to look at this first one, maximum height. And so if you think about it, you think about this ball kicking, he kicks a field goal, and it reaches a certain height, and then it falls back down. If we take a look, let's say I was a football player or a referee standing right behind this football player, and I just was looking straight behind him, you would see the ball, and look at my pointer, go something like this. It would go up, and then it would go down. And so if you imagine that, at the maximum height, what is a y velocity? Well, our y velocity at the maximum height is going to be 0. The ball literally will pause in the air before it starts coming down. It will be 0 meters per second. So we're going to assume that in the y direction. So we're going to use this equation because we don't have time. Notice we don't have any time in this reaction. The only equation that we don't have time in is this last one. And so we're going to assume that Vf is 0. We have our initial velocity in the y direction. We have 2 times the gravity, and then we're solving for delta y. So if we solve that, we take the square root of 13.5, multiply 9.81 by 2, get that. Then I'm going to subtract that to this side, subtract the 182.25 to that side. I want to isolate y. I'm going to divide both sides by 19.62. And I'm going to be left with 9.3 meters. So at the maximum height, this kicker kicks the ball 9.3 meters in the air. So that's our answer for A. Our maximum height is 9.3 meters. Now, how long did it take the ball to return to launching height? So not to the max height, but to launching height. So basically before it hits the ground. So how do we figure out that? We're solving for time. Notice there's two different ways we could solve for time. We do have the delta y, but you probably don't want to use that second equation because you're going to end up having to use quadratic formula. You could use it, though, now that we have delta y being 0. But I'm going to encourage you guys to use that first equation. So our first equation is this. We're going to assume that the final velocity is going to be the same as that initial velocity in the y direction, so 13.5, just opposite. So our final velocity is negative 13.5, right, because it's going downwards. Our initial velocity is 13.5 meters per second. And then our gravity, again, acceleration to gravity, 9.81 meters per second squared. Okay, so I subtract that to that side, so we get a negative 27 equals to that. Time is going to be 2.75 seconds, and that is how long it'll take the ball. That's the total air time of this kick, 2.75 seconds. So the last one, how far away did it land? That is actually an x component, x dimension problem. How far away did it land? So we're going to have to look at the x dimension. We have one equation in the x dimension, and we're going to be looking for delta x, the total distance traveled by that ball, the total displacement. And we already have Vix, which is 23.4, and our time we now know is 2.75 seconds. So we have that, multiply them together, our total displacement is going to be 64.4 meters. So this ball is going to be kicked that far, that range. Okay, and so that's how to do the second type of problem. Notice again, just to summarize, we start off by dividing into our components, and then we're usually going to have to use the y dimension to solve for a few things before we get to the x dimension. Okay, and so always ask yourself, which dimension is this working in? Is it the y dimension or is it the x dimension? Okay, and that will help you big time. So thanks for joining us, and we will see you next time.